pleasure to introduce Ida Momennejad, who is currently employed at Microsoft Research. She's principal researcher there and has an extremely rich and unique background. She has a software engineering degree from Tehran, a PhD from Berlin in computational neuroscience.
Master's in philosophy.
A master's in philosophy of science, I remember. From the Netherlands, is that right?
Okay.
And has been a postdoc at Princeton most recently before, and I think a position at Columbia before moving into the tech world. And is a frequent presence at philosophy conferences, and her work in AI and is as interdisciplinary as her educational background, and I guess could be summed up as understanding how both humans and AI model the world, which I guess leaves open a lot of options. And as I learned today, is also an artist who exhibits her work at extremely fancy places throughout the world. And I'm not going to list them all because we want to hear you talk about your research.
Thank you so much.
The floor is yours.
Thank you for that gentle introduction, and also thank you everyone that I've talked to today. I was very impressed with the interdisciplinary conversations we had. Today I want to show you a little bit of my work across different fields that might be interesting to you guys. Not all of it, but some aspects of it. And because there is a lot going on, I wanted to suggest that we leave questions for the points where I say questions in the middle in different times, just to make sure we can pace the talk throughout. So before I get into the kind of the brains and AI part, I just want to say my general question that has driven me across different disciplines is, how can we understand the intelligence and long-term agency of living minds? And I don't mean this in terms of a maze you want to get out of, or a complex chemistry problem or protein folding problem you want to solve, but I mean at individual, collective, ecological, and civilizational scales. What can we learn using neuroscience, modeling, philosophy, about how it is that living intelligence roams around and gets to shape entire worlds, maybe bigger in the future, more than our Earth. And I'm very interested in how this current moment of automation of minds plays into it. But I'm going to focus on a smaller part of this question. In the discussion afterwards, we can link all of these things together. And I just leave that question as a provocation so that you can keep those questions in mind. I'll first tell you a little bit about aspects of what I just showed you, that question, that have to do with the way representations are shaped, memory is shaped, knowledge is shaped in brains at multiple scales in order to exercise agency and prediction over the world. And then second, how that work informs the way we understand and steer what we call reasoning in artificial intelligence. Okay, to that first one, the question I've asked for a very long time across different research projects is how the brain structures the past experience in order to shape representations and algorithms of memory, prediction, reasoning, planning. So this relationship between the past and our experiences, and how that experience is restructured in memory, and how that knowledge now is retrieved, pieced together, and transformed in order to plan the future. This can be in the navigation domain. It's easier to imagine it in the navigation domain, but it doesn't stop there. Any area in which you have some sense of hierarchical representations, this applies to. If you want a screenshot of taking a look at some of the relevant papers here, I'll talk about some of them, but not all of them. Recently, we had a book, Space, Time, and Memory, from Oxford University Press, and I have a chapter there that summarizes some of this. The book was, again, it included neuroscientists, psychologists, and philosophers. Overall, it seemed to me what I saw in different brains was a multi-scale predictive representation structure is the shape of memory that enables prediction and planning. And that's what I will first tell you a little bit about. Okay. In 1948, Tolman wrote a very beautiful paper. He summarized 20 years of research that went against the behaviorist dogma of the time. The behaviorist dogma was biological things learn things when they are reinforced. Positive, more, negative, less of this. Tolman said, no, I think they learn even without reinforcement. And what he conducted an experiment in order to solve that problem or address that question was by putting the rodents inside a maze for a couple of days and then introducing a reward. This is one group. Another group, the rodents are put in a maze and the reward is already in the maze. If they only learned something when rewards were present, the two groups should learn the path to rewards on that 7th day for the first group and the first day for the second group in equal time. But actually, the group that had been roaming around the maze without receiving any rewards could learn this faster. And Tolman took this to mean the brain is learning something. So inside the input and output, there's something else going on that's mapping the structure of the environment irrespective of rewards. And then 30 years after that beautiful paper, O'Keefe and Nadell had a book, Cognitive Maps in the Hippocampus. The early paper was cognitive maps in rats and men, then you have cognitive maps in the hippocampus. And this is after John O'Keefe finds out that when a rodent passes the same location, similar cells are firing in the hippocampus. He called them place cells or place fields. There is a field, and every time I pass within this field, a certain cell is excited about this. And then 30 years after that, you have a paper by the Mosers, who then show that there are grid structures in the entorhinal cortex, where I step here, an entire grid shows up. And every time I'm in any point of that grid, the whole thing shows up. Together, they won the Nobel Prize in Medicine in 2014 for what they called the GPS of the brain. Now, what they did not address was, what is the shape of this map that is learned inside the brain? Is it one-step maps that I have stored, this leads to this, this leads to that, and then when I have to reason and make inferences and I need to plan, I just roll everything out one step at a time? Or have I cached some multi-step dependencies and I do this jumpy way of thinking about the future and fill in the between later? In reinforcement learning, which is the modeling paradigm that I use a lot, it's a modeling framework where an agent is supposed to take actions in an environment in order to maximize value, just to put it very simply. But then you have model-free and model-based reinforcement learning, and I'll show you a little bit of that. This one is closer to model-based RL, which you will see very soon, and this one is closer to successor representation, which I will talk to you about later as well. But right now, let's hold on this one-step, multi-step representation idea. And I just want to, like, in an abstract way for those that prefer this before getting into details, to show you this. Imagine the sequence of experience. You can imagine this as locations. You can imagine this as a series of tokens or letters. You can imagine this in terms of different smells. It goes A, B, C, D, A, B, C, D. This sequence, let's say, keeps repeating itself, right? The one-step way of learning this or remembering this would look like this. A, B, B, C, C, D. When I have to make an inference or plan, I just unroll them and make inferences. I'm like A, B, then B, C, then C, D, therefore A, C. A, C, and C, D, therefore A, D. Does that make sense? So I have to unroll. At the moment of decision, I have more compute to do. But with this one over here, I am storing the one step, but also with a little bit smaller, you can see this, I made it a little smaller. So with a little squint, I also have that multi-step association. And with a little more squint, there's also this one. What you would see in the equations that come, there is this gamma parameter. And it's basically going like a little bit of a exponential decay over the future. So I am squinting and I see some part of the future more than just a step ahead of me, right? This small thing, what does it mean? It means it's already cached some inferences within my predictive horizon. And that predictive horizon is determined by that parameter gamma between 0 and 1. Where I'm saying I'm just going to still see a little bit of what is after and a little bit of what is after. So if neurons are learning like this or are learning like this, in these neurons you would expect that after learning associations, when I see A, B activates a little bit, but that's it. C doesn't get activated. But in this one, when I see A, B gets activated, C gets activated a little bit less, D gets activated even less, but they're still there. The traces of that kind of future is still there. So that's the biggest intuition, the cached inferences versus only one-step dependencies. Okay. In my work, how do I approach understanding and analyzing the behavior of a model and comparing it with humans? I do not equate them, and my last slide of the whole talk at the end you will see, I don't think that these are equal. I do think there are mathematical principles that could be allowing abstraction across the agents and in brains. And I try to look for those common mathematical principles without equating any of these agents with brains or with human likeness. All right, so between humans and selected RL agents, if we want to compare something, we want to come up with some tasks such that we know these tasks would elicit different behaviors from the different agents that we are comparing to each other. And then we can see which one of them produces behavior on its own. This is not model fitting. This is creating some algorithmic agent that will do certain things in certain conditions and seeing whether the behavior, according to some measures, looks like human behavior. And this is by using accuracy, errors, reaction times. Later you will see I will also look at what are the steps that were done in this, what we call in reasoning or inference steps. Second, once you find the winning model here and the right experimental paradigm and the right behavior, then you can look at the neural responses. I've used fMRI and electrophysiology myself. Other people might prefer eye movements. They might prefer EEG. And then we can have a behavioral and algorithmic / representational comparison between the two. The candidate RL agents that I'll describe today, if you're mathy, you're welcome. If you're not, that's okay. I will explain these in detail. I just want to say this. This one here is called model-free because the only thing it learns about the world is the value of states and actions. I've made it simple to be V of S. So every time you see V of S, it means value of state S. State S could be this room. And then every time you see alpha, that's a learning rate. Every time you see R, that's a reward. Every time you see gamma, that's the squint parameter. But this guy only cares about a kind of a running average of value of places and actions. It does not think, or I shouldn't use the word think at all, it does not maintain a relationship between the different states. Like, what is the map of this building? Has no idea about it. These two guys, they do. And we will talk a little bit more about them. When we go back to the Tolman example, these are the guys you want to hang out with if you believe in Tolman's experiments, basically. This one allows you to stay in behaviorism. So if you imagined humans are exclusively model-free, you would be a little bit more in the behaviorist domain. So what is that behaviorist one? Remember, there's no map. What you're doing is your state S, you take an action A, you see reward R, and you go to state S prime. I arrive here, somebody hands me coffee, great, and then I take an action of coming here to this room, and this is S prime, and then there's a reward here. People are listening to my work. And then the learning rate is between 0 and 1. This discount parameter is between 0 and 1. And what is this orange parameter called? Anybody, this orange phrase here? Anybody? That's the reward prediction error, exactly, or value prediction error. Let me actually put that here. The temporal difference learning prediction error became very famous because in 1996, there was a famous neuroscience paper showing that there's a link between the function of dopamine and this value prediction error, or temporal difference learning. What does it say? It says, what did I expect to get here? And what did I see? which is the reward. And what do I expect to get after this, which adds to the value of this, but squinted, right? So I go to holiday, I go to, I don't know, I go to Bahamas, I'm expecting a lot of good things, right? So there is a gamma of a very giant value in front of it. If it's a very sunny and it's a very rainy and muddy day, this is going to be a very large negative prediction error for me, because what I'm observing and what I expected does not make sense with what I'm actually seeing, right? This is very fast because it only caches expected value. So at any stage, I'm like, this is good, this is bad. I can make a decision very quickly, but there is no map. So even though it's fast at decision making, it's not flexible. When there's something small in the world changes, you tell me, oh, that room is closed or that corridor is closed, take another one, I'm lost because I haven't had other approaches to the map. Model-based reinforcement learning, on the other hand, and imagine this is the world. I go to room 1, it takes me to room 3, 5, and then from the lobby, I can go to room 2, then 4, then 6, then get some money. This one stores separately a map of the environment. That's the one-step map that we talked about. So it only stores one-step relationships. Like 1 goes to 3, 3 goes to 5. And separately, it stores a vector of rewards. It says, okay, if you're in this state and take this action, this is the reward. But it doesn't have the future discounted value, right? And then at the moment of decision, you need to unroll a lot. Every time you guys see V star, it means the optimal value. So V is just the value of a state, and an action. V star is the best value you can get there. So here, I could do jumping jacks, or I could give you a talk. The value of doing jumping jacks is probably lower. The optimal value for this moment for me would be to do a talk, right? So that would be the action with the optimal value. The optimal value in state S, how is it arrived? By max A, choosing actions that maximize value. That's the max A over here. And by that, maximizing the expected value of the following states. What are the following states? Each of them has like a discounted to the power of the, the number of steps from here. R of that state, given that you go into that other state and take the action. And what action? You take the action that maximizes this expected value, right? This is the Bellman equation. And you can do this Bellman equation in a model-based way by turning this expected future value into something that takes into consideration probability of going from some state to another state, and taking the value of the next state as well. So the whole one-step map of the world can be summarized with this simple thing. Probability of ending up in state S prime, given I started in state S and took action A. Does that make sense? Okay, good. A lot of nods. Now this is very flexible, but it requires iteration. You have to do that thing, go to this, go to that, just iterate over and over, compare values. It's a lot of work at the moment of decision, but it has high flexibility. Now, if you're an animal running away from a lion, you might not have time to unroll every possible step and do all the Bellman equations before you can choose which way to go. You might want to have cached some inferences already, right? Another way to store the map of the environment separately is with the successor representation with a multi-step map. You would see a pi here and a gamma here. The pi means some policy. Policy is simply a sequence of actions, right? Optimal policy would be pi star, which would be the sequence of action that gives you the optimal value, right? So every time you see star, remember that's the optimal. So, and pi, it's just beginning of policies, P. Very simple to remember. So what is a policy? This is a policy. I just went from there to here. This is another policy. Does that make sense? So a sequence of actions that takes you from some state to a kind of a terminal state, which is kind of meaningful. And what's stored here is, instead of one-step associations, you have cached the gamma times the probability of transitioning to these next states for the relationship between 1 and 5. And what does it give me? It gives me the average expected future occupancy, the counts. How many times, how often do I expect to visit the state within a given horizon? And what's that horizon? That horizon is determined by gamma. So on average, within the next half an hour, how often am I going to go to the other side of the room? That would be the successor representation. So it's different from probability, which we had in the last one. Probability is between 0 and 1. This value can be above 1, right? But it has a relationship with it, as you can see. The relationship being you have the probabilities multiplied by each other and multiplied by gamma, right? Then what do you get after all of this? What you get is this, and I will show you, for those of you who are into graph theory, this is like reachability. This is basically like multiplying adjacency matrices by each other, but that's if the probability of everything was 1. What it tells you is from a node that is not adjacent to another node, to a node that is multi-steps away, how often do I expect to get there if I was taking a policy? If you're taking a random walk, this would collapse into I minus gamma t inverse, which t would be that one-step map that we talked about. So t would be that one-step map, which would have the probability of going to state S prime, given you started in state S and took action A. And then m would, under random policy, if I equally visited everywhere, or a uniform policy, would basically be identity matrix minus gamma t inverse. So that's the relationship that they do have with each other. But in most of life, you don't first go everywhere and then decide, okay, now I'm going to inverse this matrix. That's not exactly how things work, right? So how can we learn this as we go? Do you remember how we were learning that last thing with the prediction error that was here? So it was like a value is updated with learning rates times value prediction error. That's how we learned in the temporal difference learning approach in reinforcement learning. You can apply the same thing, but instead of value, you can learn a row of successor representation. And you can initialize it with total 0 or random or identity matrix. And then you go, all right, I'm going to update it with some learning rate and a successor prediction error. And what does that say? It says, I arrived to a state S prime, so I'm going to add 1 count. So this is a count base. You count how many times you end up somewhere. Plus what I expect the future of this to be, where do I end up from here, minus what I expected from the beginning. So a successor prediction error. Is this the future I expected in the past, right? So imagine like this. You are inheriting the discounted future of the new state you arrived at. So think about migration. You go to a new city, you go to a new country, you're expecting to inherit some future that is possible from there that might not have been possible somewhere else, right? Maybe this is a good intuition to remember it. This is the future you're inheriting, the structures, not just the value, the places you can get to from here, the places you can expect to be at from here. And then at the moment of decision, then this is the beauty of it, you have a linear combination of the row or the matrix of M with R, which is a much faster computation than the iterations of the Bellman equation. So what does this cached inference allow you? It allows you to basically pre-bake your decisions and just quickly microwave it at the moment of decision instead of having to do everything from scratch. Now here's the beauty of this matrix that we just talked about. If I laid out the successor representation M as a matrix for you guys, the rows of it, what they give you is what comes next. These are the successors. Hey, from 2, I'm going to end up in 4 and 6. That tells me something about the environment, right? The columns of it tell me, what are my predecessors? How did I get here? So in one simple mathematical structure that you can learn from experience, or you can create it from knowing just the one-step associations, you suddenly have the past and the future at the same time. Now you have a shape of memory that allows for prediction readily. You have a predictive shape of memory. Does that make sense? Okay. Another nice thing about this is if you can compare them side by side. So you still have a separate map and separate rewards. So you can move around the rewards and be flexible. You don't need to do all the iterations. You can do a very simple kind of operation here. And also, you have some ready pre-baked inferences of what are the multi-step things that can end up with each other. That being said, you also need to sometimes update it. And because updating of the multi-step dependencies needs you to go through them, I came up with this kind of combination with the Dyna architecture, which simply all it does was that it would replay certain things from your model of the world in order to update your Model 3 learner. So it was like a hack that was introduced in the 90s, the Dino architecture, so that the Model 3 could be a little less, a little bit more wary of the structure of the environment. And that was obviously a loss. I should have called it dinosaur. So from now on, I'm just calling it dinosaur. So you will see this. And you will see very shortly why this matters. One more thing I want to say. Remember those place cells and grid cells we talked about? This beautiful mathematical structure that can capture the past and the future, its columns also capture some property of place fields, which is they get skewed towards the location of your goal. If you go in that direction for a long time, place fields in the hippocampus get skewed towards that direction. Also, if you get the eigenvector of this matrix, you get grid fields, which is pretty great. And we did some more acrobatics with it, and we get distance between cells, distance to goal cells. So mathematically, it's a very rich structure. It allows you to do many different things. All right, now, and if you want, you can check some of these examples here. Now, which models predict human behavior better based on all of these things that we talked about? So we have some different structures or so some different tasks that can help us understand better what are the differences here. So imagine you're taking a flight. The reward structure of the world can change. The location of the coffee cart can change. The location of your gate can change. But we are very flexibly adapting to that. In an experiment, we had people navigate certain sequences over and over and over. It was similar to that ABC example I gave you guys, right? At the end of phase 1, if I ask you, do you prefer state 1 or 2, which one would you say? Exactly. And then in phase 2, without going back to 1 and 2, you just observe local changes at the end here. You do not go back to 1 and 2. And then in phase 3, I drop you back to 1 and 2, and I say, which way do you want to go? What should you say now? Can Model 3 do this? How many people think it can? How many people think it cannot? The room is correct. The reason is it needs to go back to 1 and 2 and experience things again to update it, right? Can Model Base do this? I see some nods. Yes, it can. Because it's separately storing the rewards and the structures, and just the rewards changed anyway. Can successor representation without replay do this? How many people say yes? How many people say no? Okay, I saw some yeses. The yes is correct. They can, both with and without replay, can solve it because the structure of the world didn't change. The only thing that changed was the rewards. So everything else is the same, right? All right, what if this thing happens that is the bane of my existence in New York, where the subway line swaps suddenly, F is running on A, 2 is running on 1, and then you end up in World Trade Center when you don't want to. That is a case of transition revaluation or changes in the environment dynamics, right? So let's say it's the same experimental paradigm, the rewards don't change, you just experience these local changes, right? Suddenly you open that door and you are in somewhere else, you're at the train station, right? Now here, can Model 3 solve it? Again, no. You guys can do this if you want. So. Can Model Base solve this? How many people say yes? Yes, a lot of people are saying yes. Can successor representation without replay solve it? How many people say yes? How many people say no? Can someone who says no say why? Anybody, why?
Because the structure changed?
Yes. And why is that important? Because the structure changed in a way that it has consequences for 1 and 2. So 1 and 2, without replay, they would inherit an old relationship that no longer exists. They are thinking about a future that no longer is possible. So imagine if somebody still thinks Obama is the president. That's the kind of you imagine a future is possible that is no longer possible, right? The local change was applied accurately, but the long-range change did not get applied. And replay can solve this because you can stitch things together with the recent experiences and the ones that the most recent version of everything that you've experienced, you piece them together, it'll get you the correct inference and you can update it. So after all of that, now we have a prediction by our different structures for these two tasks. One-step model-based will be equally performing just equally well on both. SR without replay will only be able to do one, and dinosaur will be able to do both, but it needs more work for one of them, so it might not always do it as well. And here's human behavior. This is a control condition. Why do we have a control condition? Maybe students can make a guess. Why do we have a control condition? Because what if people just forgot what they were doing? In the control condition, when things don't change, you can see how do they behave when nothing changes before seeing what is the difference between two different changes, right? This gives us confidence that, okay, these people were actually not just randomly changing their behavior. So this makes this difference meaningful. First of all, we know that this cannot be successor representation alone because this is not zero, right? It cannot be model-based because these two are significantly different. Also, that difference is not just because of speed-accuracy trade-off, because actually this one took longer, not less. And it's less accurate. What does that mean? When we have something that takes longer and is less accurate, what does that mean, students?
Worse.
And what does that mean in terms of what the mind had to do?
It's more work.
More work. What was it doing? That's the place where these theories come in, right? Maybe it was replaying certain things, maybe something else, and now we can test those things, right? And in fact, there is a positive correlation between how long somebody took and how much they corrected their past behavior. Okay, I'm sorry to take so much time for such a small experiment, but I wanted you to understand the logic of mathematical abstraction in ways that we are not reducing human behavior. We are really just studying a very small thing and trying to understand how that applies using these computational models as more precise theoretical tools. So in some ways, you can see this as a computational hypothesis rather than imitating the mind, so to speak, right? We replicated this with different kinds of decision trees. We showed that these capture some neural responses in patients. I'm not going to go into detail because I have a lot more to show you guys. Some colleagues of mine showed that this dinosaur also better captures rodent behavior as well as human behavior in larger mazes. Something I will show you guys, though, is this work that we did with Eva Bruneck, where we got, I also studied I had a 2018 eLife paper with using fMRI to analyze the replay to show that during that period where there was more time being passed, that actually what was being replayed by decoding it from their brain, basically. So that's another one you could take a look at. In this one, we wanted to see whether this actually scales up. So not just in this ABC small cases, but city distances. So in this case, we took some data from folks in Toronto who had people lie in the scanner and look at this kind of realistic Google view images of the city and either navigate to a place they knew in a goal-directed condition, so they were using some kind of a map in their own head in order to navigate, or they were in a part of the city that they did not know, and an arrow on the screen was telling them which way to go. Our hypothesis was that when you know where you're going, your brain will show similarity to further distances in terms of the goal, so to larger predictive horizons. And we expected this to be in the form of like a gradients along the prefrontal cortex based on some previous work I had done, and along the hippocampus. And how we did this was, as they navigated in first person, they never saw this map. We extract the kind of the path that they took. And remember what we called this in reinforcement learning? Policy. This is an example of a policy. Take their brain when they were in this moment, and their brain when they were in this location, that location. And then try to see which of them correspond to our hypothesis. And I'll show you in the next slide. But before that, I just want to say the gammas we were talking about If they're 0.1, they correspond to roughly 25 meters. And if they're 0.9, they go up to almost a kilometer. So it's a very large distance between the predictive horizon of these gammas that we were talking about. This makes concrete a little bit the abstract idea of the squint parameter I was telling you about. So how do we test that? So basically, the successor representation is a kind of a discounted expected future visitation, right? So the hypothesis would be that my brain scan at TRT, TR meaning repetition time, every time a whole brain is scanned, would be similar to the weighted sum of future brain scans in locations T+1, T+2, T+3, and T+n, right? And the gamma parameter would determine how many of these are really meaningful, and then it turns into 0, right? So if you have something that is a smaller gamma, this will kind of fizzle out here. If you have a larger gamma, this will fizzle out further, if that makes sense. So you see different predictive horizons. And what we observed, I'm not going to show you the hippocampus, but just the PFC in the interest of time. So this is what I was trying to draw on the other one. This is how many TRs into the future you actually get with these different gammas, right? So you get pretty much like close to 40 TRs with the larger gamma and almost like 1 TR with the first one. So it's a one step almost versus many steps. And what you see is that in the GPS condition, where if you just look, you can see up to a couple of tens or hundreds of meters, depending on whether there is a turn on your path, right? In the GPS condition, you only get similarity to things that are within that horizon, within kind of visible horizon. You don't know where you're going. In the planning condition, you get up to further steps that are behind the twists and turns that you cannot see. And the reason is because you are navigating from your mind. You know which way you're going, so to speak. And what you see is a gradient where the more anterior prefrontal cortex, my favorite regions, like Brahman area 10, that area seems to be a lot more interested in larger horizons, as opposed to like slightly more posterior prefrontal cortex areas. And it's very interesting, even in the orbitofrontal cortex you can see, and some people think that OFC and ventromedial prefrontal cortex are where cognitive maps meet value, whereas when you are a little bit more dorsal, this is where you have just the abstraction, so to speak. We also did some more work showing that multi-scale predictive representations, you can do a little bit of fun math with it, with the inverse of the Laplace transform, and you get some structures that explain bad data. Because we first did the math and we're like, how do we test this? We showed this to some colleagues and they said, oh, somebody has bad data for this. It was wonderful. We also found rodent data. So this is the nice thing sometimes about doing, I guess, math philosophy or math hypothesis. You make predictions that you can find sometimes similarities to in data from biological entities. We also did a 3D version of this work that we are going to submit soon. This is collaboration with Paul Fletcher, with whom together we are advising Millie, grad student at Cambridge. We were also here simulating how the surface of switching from 1 and 2 will change as a result of not just learning rate during experience, but also learning rate during replay. So what is that sweet spot of how much should you update from replay and how much should you update from experience? If you update from replay too much, you might border on psychosis. If you update too little, you might be rigid and not flexible. So what is that sweet spot? And our goal is indeed to study psychosis. And that was part of the reason to gamify this in VR, because it would be easier for patients to hold their attention for a longer period of time. When people come out, we ask them to draw a map. We also we also give them a questionnaire to see if they're more of an allocentric or egocentric kind of spatial reasoner. To our surprise, people are pretty much split in half. And how they responded to the questionnaire predicts how well they draw the map, whether it is an inaccurate or accurate map, and a lot of their behavior. So that was a very fun thing that we are going to put out. And we think this has very interesting applications, especially to understanding psychosis. To wrap up this part, there are some predictive representations, and they are, it seems like across not just our work, but other people's work, including context and episodic memory, optimal sub-goal setting in hierarchical RL, spatial navigation of place and grid cells that I told you about, statistical learning. There are different domains. It seems like this kind of, the shape that I showed you guys, this predictive representations might offer some kind of a general principle for memory organization in ways that lends well to prediction and planning. Okay, the next part is the AI part. So before I get into that, there's 3 studies there. Just want to pause to see if there is any questions. If not, you can leave it for the end. We're definitely going to discuss more. If everybody consents, I can move on. Yeah, awesome. So the second part is about algorithmic evaluation and steering of reasoning in generative AI. And I personally don't think that, I think we should always have like quote when we talk about AI reasoning, if that makes sense. Some people might disagree, and hopefully we can talk about that. Pretty much every day on your screens, you're seeing something that comes out. Oh, Microsoft says AI shows signs of human reasoning. Oh, I don't know, large language models have a reasoning problem. They're hallucinating. Some glimpse of AGI, I don't know, like flicker of AGI and sparks of AGI and embers of autoregression. There are all these different papers that come out. But what are they actually doing? When they do solve a problem that we consider a reasoning problem, what are they doing? First thing that we did in 2023 was CogEval, which is a cognitive science-inspired framework for evaluating cognitive capacities of large language models. We tested it on 8 different large language models. This is in March 2023. And we designed a series of experiments to evaluate their ability to reason in multi-step ways. And the way that CogEval works is you first operationalize whatever latent ability it is you're interested in terms of different tasks that can be measured. And then you can design, for instance, different graph structures, different item domains. We try both spatial and social. So for instance, I could say, room 1 leads to room 2, leads to room 3, or I can say, Ida is friends with Susanna, Susanna's friends with Michelle, Michelle is friends with John. If Ida wants to pass a message to John, which path should she take, right? So you can very easily turn the exact same graph structure into a social network, which we do, because it's important not to stay in one domain. And then generate instructions, prompts, many different task conditions. We do 15 task conditions in 5 categories. Many prompts, do statistics. You guys are familiar with this. In the ML world, unfortunately, many people just take some, especially back then in 2023, people would take some observations without doing full stats or controlled conditions, and they would draw very strong conclusions, if you can recall. And I think anybody who's the cognitive scientist here probably has grunted at the screen when you saw those things. So this was kind of our attempt at a grunt in the shape of a paper. And here are the different structures that we considered. This guy you already saw. This one you already kind of saw, which we did in that same paper. This is just a longer version of A. This one was in a statistical learning task from Anna Shapiro that we extended in another paper of ours, and this is from one of my collective memory studies. The way we would explain a graph structure is because they're not seeing things. They can't just like see different rooms. Was like this. Imagine a building with 6 rooms. From the lobby, you can go to room 1, then 2, and then from there's this much money, and then from lobby, you could also go to room 2, 4, and 6, and there's $50. Now, if you wanted to go from the lobby to get the most amount of money, what's the path to go, right? This is graph A. The domain is spatial, and the condition is value-based planning, for instance, right? Now, I have a question for you guys. Okay, let's say from A, B, and C, which one do you think would be more difficult for an LLM to do? To start from somewhere and then find the optimal path to the highest reward. Which one would be harder? How many people say A? Raise your hands. B, raise your hands. C, raise your hands. Nice. Okay, between D and E, how many people think D? How many people think E? The majority is wrong. So before I reveal the answers, here are the 15 tasks. They are categorized in traversal, which is go to the optimal value, or the path is a 1-step path, I just say go from A to B, or it's a 2-step, or it's a 3-step, or n-step. These are the non-value, and this one is based on find the optimal value. Reward evaluation, policy evaluation. You saw these things before. Transition evaluation, you saw it before. We have it stochastic and deterministic. Teleportation, non-teleportation shortcuts, shortcuts versus detours. But the general category is detour, shortcut, transition evaluation, reward evaluation, and job traversal. And here's what we observed. First of all, I was very surprised that things were so low. Back then, everybody was like, oh, GPT-4, like, this is the next whatever. And then I was like, oh, it kind of peters out very quickly. If we had only looked at one graph, we would have said, you could have made all these conclusions that the newspapers were drawing, right? Yes, they are close to ideal in terms of planning, etc., but that's not really where you stop if you want to do controlled experiments. You see, the graph C, which is just a longer version of A, already is a huge drop in performance. Why do you think that is? Anybody has a guess? Why would C be so much worse than A if the only thing that it has is just a little longer? Anyone?
Just memorizing. I feel like it would be just exponentially harder to memorize a longer chain of things.
What else?
We didn't need to go back to the beginning for every additional block.
No. It's a lot simpler. You guys are frustrated with it. It hallucinates. The longer the path gets, it starts to make things up. So if you ask it, what are the one steps? It remembers that. But when it needs to stitch them together, it starts to hallucinate the longer things get. What about this one? Why is graph B so hard? It's a small tree, it's just 2 steps. Why is that one so hard? Look, some of them, 3 of them are flatlining already at B, and B just has, it's a 2-step tree. Why is this so hard?
Confusing.
Say again?
Confusing.
Why?
And mix their steps together. Kind of like hallucinating. Like misremembering.
No.
It's just more conditional probabilities,
What does that mean?
which means there's more. A doesn't necessarily mean B. It just means it could be B or C. So it's like half as likely to hallucinate.
It's not about hallucination anymore. It's about why does it find it hard? It's just 2 steps, you know?
Because it thinks probabilistically.
Okay, that's actually getting closer, because if you get one thing wrong here, you get one edge wrong, it's done. There's only, you have to be very exact. But as you can see, this little guy, this E, which has so many edges, it's easier actually than B. For some of them, not for all of them. For this guy, they are almost the same as each other for some of these, right? So for some of them, B is easier, but for some of them, it's at the same level or sometimes even easier. The reason is that there are many paths between 2 nodes. So if you're taking probabilistically 1 out of the 4 paths, you can still make it. But with this one, you take the wrong one, it's over. There's no going back. It's a one unidirectional graph. What about this one? Why is D so much harder than E even for GPT-4? Actually, for GPT-4, you can see that E was easier because you can kind of make it. Why is D so much harder? Because you have these bottlenecks. If you don't pass the bridge ties, you're not going to make it. When it's very important that you pass something, otherwise there is no other way, it's very hard for it. It's interesting. When there are multiple paths, and this speaks to the probabilistic thinking, right, which is somewhat related to what you were saying as well. But you guys see how just by looking at its behavior on these graphs, we can already get some inferences and hypotheses about what else to test about what algorithms it's using to reason, right? You guys can see that. Just behavior can give us insight into cognition. Now, what are the failure modes? That's the structure. What is this failure mode? We just talked about it. In the answer, it's generating a path between 3 and 12 that doesn't exist. That's a hallucinated path. And it really didn't need to do it. What about this one? When you ask it, list the one-step paths, it does list 7 to 8. But when you say, what's the shortest path from 1 to 7, when you say, what's the shortest path, it's going like a detour. It's not giving you the shortest path, even though it has it. And with this one, what happens here? What is the failure mode you see here that's new? You see still the hallucination, but you see something else too. What is it? It's a loop. A shortest path should not have a loop. So these are the failure modes that you observed. Now, with all of these things that we saw, oh, I need a lot more. Please, 10 more minutes. Yes. Okay, I'm going to ask questions less, but it's really fun when you guys engage. Okay, so how can we evaluate the algorithms now? So in 2 other projects, one was the ICML paper, that came out in the winter. We need an algorithmic evaluation of generative AI. And then this one that we submitted, and you can find it online, and it's the title of this talk, which is the kind of compositional geometry of reasoning. We tried to open up, and by the way, special thanks to Institute for Pure and Applied Math at UCLA. This was at one of their winter retreats, and this is 4 of the students are their undergrad interns. What we wanted to ask here is, okay, now we have some hypothesis about how they're solving these reasoning problems, but can we use our neuroscience and math expertise to go deeper? So if we analyze the inner layers, do we find some kind of an emergent search algorithm? Is it like a forward search? Is it like a breadth first search? Is it like a depth first search? Is it something else? And can we sort of use these inner layers in order to understand it? So in AlgEval, we propose this idea that we can use similarity analysis, causal interventions, attention analysis, representation analysis to test hypotheses about certain algorithms, whether they're using it to solve that problem, but also to just figure out what are the algorithmic steps that they are really taking. Now, I'm going to try to speed up, but there are some definitions that are important here. When I say algorithmic primitive, what I mean is, what is a minimal computational operation that you can observe in a reasoning process? For instance, in the traveling salesperson or TSP, you can observe nearest neighbor as one of the operations that happens. You can break down nearest neighbor into smaller ones. So maybe it's not the smallest, but we assume that there is a hierarchy of these algorithmic primitives, some of them forming together in order to solve problems. They can be identified both in the explicit reasoning traces. If you just saw what the LLM is saying, you should identify when is it using nearest neighbor potentially, but it might not be that verbose, so that's okay. You can also find it in the internal activation, which I will talk about it. Primitive composition is when there's a combination of multiple primitives in order to express a particular algorithmic approach. And then algorithmic tracing would be the process of identifying all relevant primitives for implementing a particular reasoning process. The idea here was that if we target the computational building blocks rather than just the behavioral outcomes, we are going to be able to better trace what are the ways in which they try to solve problems and how they learn to generalize and how is it different between a base model and its reasoning fine-tuned version and so on and so forth. The insight here is that a transformer keeps a running scratch pad, imagine like a whiteboard type, a scratch pad vector for every token at every layer, like as 30 layers, 40 layers, 80 layers, whatever you have, depending on the size. This is called the residual stream. The residual stream both has attention and MLP layers. Everybody knows what these things are. So you have the attention that goes in all directions, and you have the MLPs, which are sort of local, they're feed-forward. Attention reads from everyone, writes one update, MLP reads locally, writes another update. The latent points are token-wise residual hidden states. So when somebody talks about the hidden states of these LLMs or latent representations, what they mean is the way these points are moving along these layers, basically. So at a given layer, let's say at layer 17, you will have X and T, for instance. So 1 point per token. And then the residual stream at layer L is the model's current latent representation of that token, right? So every layer, you have a different representation. You do something with it, some transformation, and the next one, that token is evolving across. So the residual stream, you can think about it as a whiteboard that's shared, and the latent representations are what's on the whiteboard right now, for instance, right? And this changes. So if all of a sudden I turn this into a star, or I turn this out, these are different things that are happening at different moments, right? What is the nice thing about this space? And this is something we just discussed a little bit earlier also in terms of the connectionist versus symbolic things, which is once you have a latent state space, then you can have some latent states that could have symbolic relationships with each other. The mechanism underlying how you can do those things are very complicated, but you can always push things into a manifold and then understand. So what if we turn this into a latent space and try to track at the same time the movement of these different things? The nice thing about it is that this is not new. Since the 9th century, when the book Algebra came out by Al-Khwarizmi, whose name inspired the word algorithm, we have had the solution to understand these things for 12 centuries. It's nothing new. So it's nice. Mathematically, we are in a comfort place. We are in home. And now we can easier try to map out certain algorithmic moves, transformations, and emergent hierarchy of states that happen at different levels of abstraction and do a little bit of simple vector algebra with them. Here's an example. On the left, you can see the verbal description of that room that I was describing, right? So given a description of a set of rooms, determine if one can get to W from the lobby, provide yes or no answer. The lobby connects to O, which connects to W and Q, so on and so forth. What you see here, this is this is TSNE, which is basically lower dimensional representation of many things at once. Every line corresponds, we are tracing one token's evolution in this space. When we say token is one thing that appears here. So if lobby appears 3 times, you have 3 different lobby tokens, right? Or if it appears 4 times here. And you can see W appears once, you have that. In the beginning, where do you see all the tokens? They're all together at the center at 0. And the numbers you see are the number of the layers. So 0 is layer 1, 0 indexed Python people. Then gradually you see a separation from them. The starting state totally moves to a different part, and everything else moves to another place. The goal node is somewhere between the starting state and everything else, and here's where some restructuring starts to happen. The interesting thing that you observe here is that in the middle states there is like a flip that happens, and the one that is sort of the better option gets closer to the goal. Another interesting thing that happens, the entire subtree over here is together. But the Q sort of branch is totally pushed further away from the original tree that it belongs to. Why is that? Why does that help? People who do memory. Say again?
Contrast enhancement?
Yes, it's competition gets lower. So you basically want to distance yourself from competition. This is similar to retrieval-induced forgetting, if people are familiar with that, which is, let's say your idea of a tree is a birch tree and pine tree, and you're equally likely to retrieve each of them 50-50. And then I keep saying birch, 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 birch. And then after a while, your probability becomes 0.7 for birch and 0.3 for pine because they were competing, they were connected. However, this has no influence on volleyball or basketball as your favorite ball sport because those are very irrelevant. Things that are competing with each other or are closer neighbors to each other are more likely to dampen each other's retrievability if one of them gets over-represented. So by pushing this guy away, it becomes a little bit easier to solve the problem. This does not sound like forward search though, right? It seems like something else is going on. We tried the same thing. That was the llama 8 billion parameter. We tried it with the 70 billion parameter. We call these things octopus plots for obvious reasons. We see similar patterns, in fact, which is interesting. We also analyze their attention patterns, and what we identify, in the interest of time, I'm going to say it very quickly, is that it seems like there is some kind of a backward chaining. Everything that arrives can look back at what came before it, because attention is basically can't go anywhere. The new token, what is the attention between that token and which of the past token that is highest? So if a lot of them are paying attention to W, which is the goal. And this W, suddenly there is this recognition that this one goes there. And since around layer, I think 15, you see up here, which is 15 because 0 index, you see that the goal, attention from this node W to goal becomes higher. This what you see here is the pattern of layer by layer attention that this token is from this token to these other nodes. And that's where also you can see that the answer starts to shift towards yes. Gonna move forward. Now, in a second paper, what we tried to do was take this state space that we talked about, cluster it, and then try to identify what in the produced reasoning traces, quote unquote, which we call them, the response of the LLM, what corresponds to each cluster, right? And then you can use topic modeling in order to figure out what they are. So you can say, oh, this corresponds to the compare or verify primitive. This corresponds to the compute distance primitive, so on and so forth. You can identify a clustering hierarchy around it. You can also look at what sequences of primitives follow each other often and form a very simple transition graph across the different algorithmic primitives for solving a particular task, for instance, the traveling salesperson. We also, so once we have this primitive vectors that we extract, which I told people at lunch a little bit, when you inject it into other tasks, they suddenly express that algorithmic behavior. The tasks that we used were traveling salesperson, AIME, which was the math Olympiad, 3SAT, and graph navigation. Why did we choose traveling salesperson? Other than being NP hard and humans being visually very good at it, 5.4 reasoning shows massively improved behavior on it compared to 5.4, which is just a reasoning fine-tuned version of 5.4, even though it wasn't directly trained on it. And what is the difference? Look how much of a big difference there is between their performance on this task that is a task that it was not trained for, right? So what we do is we identify algorithmic primitives, and we also try to validate them with causal methods. So here is, you can see for traveling salesperson, the t-SNE of the latent space, then at a particular layer, then you can see how, for instance, I've identified certain clusters of algorithmic primitives there. And then you can look at the evolution of each of these primitives across the layers. And then you can look at what are the different algorithmic expressions, different expressions that lead to the different behavior, let's say of 5.4 and 5.4 reasoning on traveling salesperson. The nearest neighbor primitive is a lot more used in the reasoning fine-tuned model. And the other one, both in terms of its primitives and in terms of its attention patterns, it pays attention to everything instead of nearest neighbor. So it doesn't do so well. And we also look at how, across all of the tokens that the answer generates, what algorithms are happening at which point of a token and then moving. So in this way, you can also look at the evolution of that transition structure of different algorithmic primitives. So you turn a solution into a transition over different visitation of different algorithmic primitives applied to a particular information across the layers. So suddenly you are moving in that latent space. You are trying to figure out what this thing is doing, what is the mechanisms with which it solves the problem by looking at walks in this latent space that is very nicely lending well to vector algebra. I'm gonna skip forward just showing you the primitive vectors. Function vectors were proposed in 2023. You give 100 examples of words and their antonym. Across all the examples, you take the top 10 attention heads that when you apply those, you get the antonym of a word. You take that out, you inject it into another word without giving any instructions, it will give you the antonym. It's also compositional, so you give a combined antonym for slow plus the Spanish translation, and the answer is rapido, for instance. So by applying these vector operations in the middle layers of an LLM, you can get it to do what you want to do with the input. So what we did was, because these are portable and compositional, we decided to find algorithmic primitives as primitive vectors. Long story short, yes, we can find it. We injected into, let me see what is the fun one to show you. Let me show you this one. If you injected You extract it from something else, so this is cross-task. You extract it from a very simple atomic task of get the first node and get the last node. And then you inject it into a second task, which is solving the traveling salesperson problem. And all of a sudden you see that when you inject that, that particular node that you injected for, its expression is mentioned in the answer a lot. All of a sudden it's mentioned very often. And you can also look at how, if you inject a particular thing, what kind of effect does it have on other primitive expressions? So you don't want to inject just everything at the same time. They have an interaction with each other, some of these algorithmic primitives. And that's also interesting. So in the future works that we want to do, we want to move towards an algorithmic way of understanding and improving. Another thing we're doing is collecting human data using the think aloud paradigm, following Herb Simon's method, which is humans solve the same task while talking out loud how they are solving it, so that we can see if we can find similar or different diverging, converging patterns among them. I'm not going to go into this. You can ask me about it later. It's just like we made a modular multi-agent architecture. I have a whole work on collective agency here. And it improved performance on Tower of Hanoi, on graph navigation, reduced hallucinations to 0. But here's what I do want to say. Let me just end here. I think we still need to make a distinction when we are having the discussion between human and machine reasoning, quote unquote. What I showed you was not to reduce human reasoning to machine reasoning or say, hey, look, these guys can do this, therefore they are the same. I think it's one thing to talk about performance on reasoning tasks, which means the outcome of the task. What is the mechanisms has to do with the process, or what are the mathematical abstractions, again has to do with process. I'm definitely on board here. But then there's the social practice of reasoning. Why are you reasoning? That is a different kind of animal, and that is not at all related to how humans or why humans would reason. And also, what is the role of reasoning for living minds? And that's an ecological ground. And they're also very different reasons. And I think this also might relate to folks who are interested in value regions and dopamine and other reasons why humans or creatures with dopamine or even slime mold would do something. I think what we do when we reason versus why we reason, it should be a question we should think about. And depending on your position, I had a paper in the Philosophical Transactions of a Real Society about varieties of what we mean when we talk about human-like cognition or human-like agents and neuro AI. And that depends on whether you care about human-like behavior only, and then the outcome would be enough. Some neural similarity of the underlying process, or some mathematical abstraction similarity where this would be enough, or some engineering problem solving where that would be enough. But if you want all of them, then you would capture up to here. And I think we would still have left a couple of things that have to do with social and ecological reasons for reasoning. And with that, I genuinely think a slime mold is more intelligent than ChatGPT. And we can definitely talk about that later. Thank you.
Okay.
Sorry about the timing.
Yeah. Questions, comments?
Yeah.
So as you were talking through successor representations at the beginning, I loved the callbacks to Sutton and Bartow, and I even want to go further back to Clark Hull. And questions about timing and sequence, maybe Guthrie. And so the question I kind of want to get at is, all of your work is based on sort of sequence, which of course implicitly may involve time, but some representations of time are the point sometimes. And so I kind of wanted to ask, is time simply a passing of internal states in sequence, or how would you represent time in successor representations?
Great question. So let me bring this thing up, the right slide to answer that. So first, time would not be the only way that we would capture the idea of a sequence. For instance, in a spatial sequence, I might wait in one room for 5 days and then go to another one. So that notion of time when you're thinking about a spatial sequence or a statistical sequence, slightly different, right? And also when you're in a graph, depending on which way you go through, even your sequence is very different. But one thing that we really thought about what you're describing, and I'm very glad that you asked, is in this work, where, so Mark Howard, with whom we did this work, he very much works on what is the shape of the past. Why do you forget things? For instance, you can remember what you ate for breakfast probably today, but if I ask you, what did you eat for breakfast last year, this time, you're like, I don't even know what you're talking about, unless it was like a special occasion. So the further you go in the past, the more things become confused with each other and the less sharp that memory is. So with these kinds of Laplace transforms, Mark Howard had always kind of had this idea of the closer we are, the sharper this thing is around the event, so the closer it is. But the further into the past, the kind of broader these become. And so I remember roughly something that is kind of a muddy version of that year, but like not specifically on one day. And we did the same thing for the future. And our idea was, if you're moving around in a world that has some kind of a structure, to the future you can apply the same thing. So our idea of time is one in which, I guess maybe it's a little egocentric. So there's something that's here, and this is, and then this person right now, it's kind of like very sharp. Here is very sharp, the predictions, but a little further it becomes more like this, and a little further it becomes like this, and likewise for the past, right? So in some ways, it's as if you're moving around in the world with some things that's, it's like the past and the future are kind of present, but the closer ones are more present. And then the weird thing about episodic memory is that suddenly my, 30th birthday is like this. Or something like, the birth of my sister, even though it's very long ago, it's like, And that's the nice thing about the ways in which the notion of time with episodic memory kind of bends on itself. In reinforcement learning, Mate Lengyel and Peter Dayan had a paper in 2008 called Hippocampal Contributions to Planning the Third Way. And this would be the third way, which is, in addition to this some kind of a monotonic notion of time, there is all of a sudden these sharp things that are those episodes that were salient.
So if you wanted to use this kind of representation structure to learn an interval, to do something after 2 seconds but not after 1 second or 3 seconds, it would follow this kind of Weber-like broader or lower precision at longer intervals? Is that the question?
Yeah, absolutely. That would be my guess, and that's like what we observe. Actually, let me see if I can. Sorry, here I'm looking for a slide. That's why I'm sort of being slow at this. Right, here. So this is what we know about free recall of a list. If I give you a list of random things to remember, and then I cue you with anything in the middle, you are a lot more likely to remember the item immediately after. A lot more likely, but less than that. That asymmetry is the reason we think there is a predictive bias in the brain. A little less, but still higher, but then it starts to kind of go in this shape. And this is one of the reasons that this thing and that other slide that I was showing you kind of makes sense. And this is also captured in the idea of the successor representation, as well as this kind of ABC slide that I had up there, right? And that's the reason why AB, which is closer, is bigger, and then C and then D is smaller, if that makes sense. The cached inferences. I don't know if that addressed me. Yeah.
I'm just going to take the bait a little bit and ask if you could explain in what way slime mold is more intelligent than chess.
I have a 1.5 hour keynote on that. Would you like yeah. I think in terms of the intelligence of life, which has to do, again, when we are asking questions, now it looks like I graffitied my own slides. Gotta get rid of time sometimes. All right, so if you think about the role of reasoning or anything else, or any of these kinds of temporal difference learning, or memory, or any of those things, why would it emerge in living things? They were not trying to make money or increase the stock market. Like that's not, they didn't have any reason. Like, what happened? They were trying to survive, but in a world that there was no individual life. You always, as a single cell, you have an entire ecology in order to even exist, let alone thrive or live. And does it help to have some memory? Yes. How does it help? Like the path to food, etc. Slime molds have a very interesting feature. It's a single cell, like at least the species I've done experiments with. This is a photo of one of my experiments, Petri dish. And this is, by the way, I tried to make a maze for it with hot sauce because they hate hot sauce. And my hope was that it will go from here like this. I was waiting for it to go here and get stuck and then come out and go like that. And it actually breaks through the wall, which is not what I expected. And this is where I was like, oh, none of my agents, my RL agents, would do something like this. This is, I think, what I kind of see as the intelligence of life, which is our agency in niche construction. We don't just receive some task from a boss and solve it. We kind of shape the task, change the task, negotiate the task biologically in different ways. We are also never alone. I have so many bacteria and fungi all over me that allow me to even exist, digest food, and breathe right now. And every intelligence is collective intelligence in the intelligence of life. There is no individual intelligence in the intelligence of life. Even in a Petri dish, this is multiple, like so many nuclei within a single cell organism that they communicate with each other. The way they ripple through the slime mold to send information, the physics of that is beautiful. The ways in which it learns, the ways in which it overcomes obstacles, solves mazes, the way in which bacteria basically slow down their metabolism or go dormant when the food source is small so that they don't exhaust their ecology, and then they come back out when the conditions are better. I identified something like 5 different principles of the intelligence of life, and they don't exist in artificial intelligence. I was very much focused in sort of that approach in identifying what is it that separates us. And like I told you earlier, I used to be a computational functionalist. I used to think, oh, it doesn't matter, in silico, in octopus, in brains, and we are all the same, just as long as the math works. But now I'm a little bit more of a maybe life chauvinist, I think. There is a difference between the intelligence of life versus the non-living tools that we have built that operate similarly on the mathematical abstractions of living cognition. And in that way, in terms of the intelligence of life, a single cell is smarter because it has the intelligence of life. And not just life, but the intelligence of life. So if I just create new life in a Petri dish, that's not what I mean. I mean something that's billions of years old, or a couple million years old at least. So it has somehow managed to claim its place in this giant ecology as a part of the bigger ecology, if that makes sense. Does that? Yeah. It's not very similar to my work in AI, but hopefully one day it will. Maybe I'll come up with some way to get ecological intelligence. Yes?
I wanted to ask a follow-up to your response to John McGann. I was really baffled by the graffiti that you now erased.
Oh, okay. I can put it back.
It's okay. I think I remember it. I mean, initially I understood your response, but then when you drew the 2 little, spikes, it just seems like, of course, there are things that happened in your past, your 30th birthday and the birth of your sister, that were striking, very memorable. And perhaps there are things in life that were very enjoyable, such that the time felt different then. But I don't know what you meant with the spikes. I don't want to read too much into.
Oh, just recall. Just recall.
Okay, but so then, sure, striking things are easier to recall. But what does that have to do with time? So your answer was about what do you mean with time and whenever there's a sequence, there has to be some. I mean, it's implied that there's some temporal element, and so what is the temporal element? But your response was about recall, and that seems to be a different issue. That just seems to be whether or not.
I mean, when we're talking about time, we're not talking about objective time. We're talking about time to the learner, I'm guessing.
Well, I was actually initially talking about literal representation of intervals.
Well, representation by whom? That's what I'm saying. But if you're talking about brain representations, human or rodents, it seems like this is the kind of thing we observe. That if you are in this moment, the next thing that comes is the most accessible for you to recall, and things in the past are less.
So when you're talking about, I guess what I'm trying to get at is,
Mhm.
or understand is what is, John's initial question was
Mhm.
just about, look, if there's a sequence, there has to be a temporal element. And then there can be a question about how you represent that temporal element.
Mhm.
And what's the connection between that, which I gather you agree with,
Mhm.
and the issue of recall?
This is that. This is a sequence.
Okay.
This is free recall of the sequence that I gave you. I gave you a random sequence.
Okay.
It has an order.
Okay.
And then I gave you one of the words as a clue, and I said, can you recall the other words now?
Sure. No, sure. I mean, I understand the concept of recall and
Do you understand the relationship between memory and time? Because I
Sure.
think that might be our difference here.
Okay. Okay.
If we are talking about a biological agent or an artificial agent's concept of time, it has to have memory. If you have no memory, you have no concept of time. Everything in a moment, that's it. And there is no remembering of what happened before or
Sure.
after.
I guess the issue that I'm getting at is,
Mhm.
memory, recall, concept of time. That's on one side.
And I'm saying there are different concepts of time depending what kind of memory is activated.
But you can have a system that operates with sequences without there being any of this, memory, concept of time, and so forth.
No. As soon as you have a sequence
You
and
have
you
to
know
have
that
that.
you have a sequence, you have
Okay.
memory. As soon as you have ABC, right? As soon as you can remember anything more than A that is at this moment active, you have memory, and that's the minimum thing you need to have a sequence.
Okay.
Does that make sense? There is no sequence.
I mean, I would just sort of distinguish between there being a sequence and you having the concept of having a sequence,
So-
which is a big difference, which
I
you
am
can have
talk-
the first without the latter.
So I am, if we wanted to have a conversation about the physics concept of time, we could have this. But I am obviously talking about biological and artificial algorithms that are capable of processing sequences. And what do I mean by that? Memory, the past, and future prediction,
Okay.
and reasoning over it, right? And what I'm saying is, one way to do that, oh, I'm so sorry if anybody has epilepsy, I apologize. I hope you don't took your medications. Okay, so one way to store a sequence is to say I'm storing A, B, B, C, and C, D, and when I want to unroll the sequence, I'm just going to unroll them one at a time. Another way is, I'm going to also cache some of the multi-step inferences. Then you're already a little out of the linear time, because I have some associations with things that are not near me. It's almost like time jumping, time traveling a little bit, right?
Sure.
Both for my future and my past.
Right.
And what I'm saying is that when you have a very, very salient or important event in the past or in the future, that also acts like a kind of a time jumping thing, like a time traveling thing, right? So if you have this, then you're always sequential, linearly exploring sequences. Your idea of time is pretty linear and sequential. If you have this, it seems simple, it seems lazy because I just don't want to do all of the work, so I'm just gonna pre-bake this and freeze it and then unfreeze it when I have to act. But at the same time, it gives me a jump to non-adjacent things. Non-adjacent dependency allows for drawing big inferences, making abstraction. This is the minimum thing you need for abstraction. If you want to say, cat, dog, a fluffy thing, I don't know, my pillow, these are some similarity between them. They're they're plushy things. And how do I abstract all of them into one category? Because of this thing happens, and then I'm like, oh yeah, this one activates, then all of it activates in some ways.
Okay.
So I think this is a very powerful thing for generalization, for hierarchy. All of a sudden you have the category of animal, you have the category of little things that are cute, you have the category of various things. So I think it's a very interesting conversation, and these two give you very different senses of psychological time, if you like. Yes?
Sorry, this might be a too naive a question, but I'm also getting really hung up on this idea. So say that I remember the birth of my daughter very vividly, but does that mean that I don't really have an actual sense of how long ago it happened? So say that the strength of my memory for the birth of my daughter is equal to the strength of my memory for what I ate for breakfast this morning. Does that mean that my perception of time is equal on these 2 events?
It means
Or-
at least there is one event that it's not the case that because it was very far in the future, you remember it less than your breakfast this morning.
I'm sorry. So like.
It means your memory is not just about time. Something else is going on.
Right. So going back to the question about what's our concept of time. So I still have a concept of time, and my concept of time, or my representation of time, to the point of my daughter's birth.
Right, sorry, if I may.
From,
The fact that you remember your daughter's birthday doesn't mean you lost all notions of time, that you cannot remember breakfast anymore. It just means just the linear time is not enough to explain your memory recall and how you connect to different times of your life. That's all. It's not an exclusive thing. It's not that you either have this or have this, and then if you have this, you don't have this. If you have this and something else. That allows you to, just because of the way you associate things, allows you to generalize. And I can add to that this thing. So, do you know about eligibility traces? How many people know about eligibility traces? Okay. So you have an event activated here, right? A. There is some kind of activation that you get, right? You have an event B that's close enough that gets also activated here. This happened while this was already a little activated. If A and B happen very often, gradually the activation of A would activate B a little bit because it expects it to happen a little bit later. And then you have C activated here, and your B becomes like this, and gradually your A becomes like this. So neurally, we have a reason why this is how that thing kind of emerges gradually. So initially, you have A, B, C individually activated, but then over time, these things get like that. And where does it happen? In the hippocampus, you have the dentate gyrus, and then you have CA1, and then you have a different kind of behavior in these ones. CA1 is one that seems to like to do fast statistical learning. It combines things. It does these cached inferences very quickly. Things have to be close. Its time horizon, as we saw, is not very far, right? But then dentate gyrus likes to separate things. It's like, no, we have A, we have B, we have C. So dentate gyrus is separate. And CA1 is like, no, let's see what goes with what. So this one is good at associative learning. This happened, that happened, that happened, combine them together, they have a relationship. In rodents, you have that in a smaller time scale. And there are studies of time in rodents, for instance, both retrospective and prospective time, up to 10 seconds. But above that is kind of hard to gauge it. In humans, you can really stick things together at many different scales, right? What else happens? When you have some kind of a representation that's a kind of an ABC muddy thing, you can also abstract them together. So it allows for what we call temporal abstraction. So you can have a representation of the same event that says, these things kind of lump together, right? Those things kind of lump together. And then you can think a little higher, and this connects it to that algorithmic geometry, right? And then you're like, these things and these things and these things, I can build something else. So you get abstraction and hierarchy once you have something like this. And hippocampus CA1 does that. And this has kind of been a very, very long-term confusion for people, how hippocampus simultaneously allows for individual events like the birth of your child versus combining things and helping for abstraction. And that's because its different subregions are thought to do different things. And also along the long axis of the hippocampus, this kind of like being the posterior, this being the anterior, the idea is that here you get like smaller steps, so you have smaller gammas, and here you have larger gammas. So your horizon kind of increases. So here you might have ABC, ABC, here you might have AZ, so to speak, right? If that makes sense. Does that kind of address what we were talking about?
Thank you.
Yeah, so I'm getting signs that time is up. So on that note, we will wrap up and move to the reception, and let's thank our speakers.